Somewhere in the darkness beyond our night sky, far past the last stars you can see with your eyes, there exists a world so large that it forces astronomers to pause mid-sentence. A planet so immense that, at first, scientists argued whether it should even be called a planet at all. A world that sits uncomfortably on the boundary between what we thought planets could be and what we believed only stars were allowed to become. Its gravity reshapes its entire system. Its existence strains our definitions, and its discovery quietly threatens to rewrite the story we tell ourselves about how the universe builds worlds. For centuries, planets were the modest companions of stars. They were secondary actors, smaller bodies circling something greater. Even Jupiter, the giant of our solar system, was supposed to represent the upper limit. 4 times the size of all other planets combined, yet still comfortably within a category we believed we understood. But the universe has never cared about human categories. It does not respect neat definitions or clean boundaries. It builds what it can, where it can, using rules that are simple in principle and endlessly complex in practice. When astronomers began finding planets beyond our solar system, the first surprise was not beauty or familiarity, but scale. Worlds larger than Jupiter appeared almost immediately, some hugging their stars, some drifting far away, some existing in environments we once believed were impossible. And then came something else. A planet so massive that it blurred into the territory of failed stars. A planet whose very existence forces a new question, not about how big planets can get, but about whether our idea of a planet was ever complete in the first place. This is not just the story of a large object in space. This is the story of how discovery changes definitions, how observation reshapes theory, and how the universe continues to remind us that our understanding is always provisional. The largest planet ever discovered does not simply break a record. It changes everything. If you're enjoying this deep dive into the quiet mysteries of space, subscribe to The Boring Universe, like the video to support long-form science storytelling, and leave a comment telling us which part of the country you're watching from. Before we can understand why the largest planet ever discovered matters, we need to slow down and examine something deceptively simple. What exactly is a planet? The word feels ancient, solid, settled by centuries of astronomy and education. Yet in science, familiarity often hides uncertainty. A planet is not defined by poetry or tradition, but by physics, formation, and function. And the moment astronomers began finding planets beyond our solar system, that definition began to crack. In our own cosmic neighborhood, the planetary lineup appears orderly. Small rocky worlds near the sun, massive gas giants farther out. A clear hierarchy in size and mass. Jupiter dominates this system not only because it is large, but because it fits neatly into a category. It formed in a disk of gas and dust, never ignited nuclear fusion, and settled into a stable orbit around a star. For decades, that model shaped our expectations everywhere else. Planets would be smaller than stars. Gas giants would resemble Jupiter, and there would be an upper ceiling to how large a planet could become before it crossed into something else entirely. That ceiling, according to theory, lies near a physical threshold rather than an arbitrary measurement. When an object becomes massive enough, its core pressure and temperature rise dramatically. At around 13 times the mass of Jupiter, something critical can happen. Deuterium, a heavy form of hydrogen, can briefly fuse. This process does not create a true star, but it does mark a boundary. Objects above this limit are often classified as brown dwarfs, sometimes called failed stars. They glow faintly not because they shine like stars, but because gravity itself squeezes them into temporary nuclear activity. For years, this deuterium burning limit seemed like a clean dividing line. Below it, planets. Above it, brown dwarfs. But nature rarely respects clean lines. When astronomers began detecting massive worlds beyond our solar system, they encountered objects that lived right on this edge. Some were just below the threshold, some slightly above. Some had masses that suggested one classification, but formation histories that suggested another. And suddenly, size alone was no longer enough. The largest planet ever discovered exists in this gray zone. Its mass challenges our intuition. Its radius defies expectations, and its origin raises questions that scientists are still debating. To understand why, we must first understand how astronomers even find planets this large in the first place. Detecting exoplanets is an exercise in patience and precision. Most planets are invisible directly. They do not shine with their own light, and they are drowned out by the glare of their stars. Instead, astronomers look for indirect signatures, One of the most powerful methods is the transit method. When a planet passes in front of its star, it blocks a small fraction of the starlight. That dip, measured over time, reveals the planet's size relative to its star. A deeper dip means a larger planet. Another method relies on gravity. As a planet orbits, it tugs slightly on its star, causing the star to wobble. By measuring shifts in the star's light, astronomers can calculate the planet's mass. When both size and mass are known, scientists can infer density, composition, and internal structure. And this is where things get strange. As planets grow more massive, they do not simply get bigger. At a certain point, adding mass actually makes them denser rather than larger. Gravity compresses the gas. The radius increases slowly, then stalls and can even shrink. This means that the largest planets by mass are not always the largest by size. Some super-Jupiters are heavier than Jupiter, but only slightly larger. Others are bloated, puffed up by heat and radiation, with atmospheres stretched thin like cosmic balloons. The largest planet ever discovered stands out because it occupies an extreme end of this relationship. It is not just massive. It is enormous in physical size. Its radius pushes the limits of what models predict. Its atmosphere is vast. Its gravitational influence dominates its system, and yet it does not behave like a star. To grasp the significance, imagine scaling Jupiter until it becomes so large that, if placed where the Sun is, it would nearly fill the space where Mercury orbits. This is not science fiction. This is the kind of scale astronomers are dealing with. A world so big that its own gravity reshapes the physics of its atmosphere, flattening temperature gradients and altering chemical reactions in ways we are only beginning to model. But size alone is not the real disruption. The true challenge lies in formation. How does something like this come into existence? Traditional planet formation theory offers two primary pathways. The first is core accretion. Dust clumps into rocks, rocks into planetesimals, and eventually a solid core massive enough to pull in gas. This process is slow and inefficient for creating very large planets. There simply may not be enough material, or enough time, before the gas disk around a young star dissipates. The second pathway is disk instability. In this scenario, parts of the protoplanetary disk collapse directly under their own gravity, forming massive gas clumps almost instantly. This method can create very large planets quickly, but it blurs the line between planets and brown dwarfs. Objects formed this way look suspiciously like stars that never fully ignited. The largest planet ever discovered may have formed through disk instability, or it may represent an extreme outcome of core accretion under unusual conditions. Or it may point to a hybrid process we do not yet fully understand. Each possibility carries implications. If disk instability is common, then giant planets may be far more abundant and diverse than we thought. If core accretion can produce such monsters, then our models of planetary growth are incomplete. This uncertainty is not a flaw in science. It is its engine. Every time an observation breaks a model, the model must evolve. The largest planet ever discovered forces astronomers to revisit assumptions that once seemed settled. It challenges the idea that there is a natural maximum size for planets. It complicates the distinction between planets and stars. And it reminds us that the universe does not arrange itself for our convenience. There is also a deeper implication, one that reaches beyond astrophysics into perspective. For most of human history, planets were points of light, wanderers against the fixed stars. They were symbols, gods, omens. In the modern era, they became objects of measurement and classification. But discoveries like this reintroduce a sense of humility. If planets can be this large, if systems can be this extreme, then our solar system may be far more ordinary than we like to admit. The largest planet ever discovered is not an anomaly in a broken universe. It is a data point in a vast cosmic distribution we are only beginning to sample. For every such giant we detect, there may be countless others hidden by distance, dust, or observational limits. The universe is not just bigger than we imagined. It is more varied. To understand why the largest planet ever discovered truly changes everything, we have to step back from the object itself and look at the environment that allows such a world to exist. Planets do not form in isolation. They are born inside chaotic, violent, and temporary structures called protoplanetary disks, vast rotating clouds of gas and dust surrounding newborn stars. These disks are not calm nurseries. They are turbulent, unstable systems where gravity, radiation, magnetism, and motion all compete, and in these conditions size is never accidental. In the early stages of a star's life, the surrounding disk contains most of the material that will never become part of the star itself. Hydrogen and helium dominate, but heavier elements are mixed throughout, forged in earlier generations of stars. This material is the raw inventory of planetary construction. For a long time, astronomers believed that this inventory imposed strict limits. Too little material, and only small rocky planets could form. Too much mass concentrated in one place, and the object would cross the line into starhood. But the largest planet ever discovered exists precisely in the region where these limits blur. The first key insight comes from gravity. Gravity does not care whether it is building a planet or a star. It only responds to mass and distance. In dense regions of a disk, gravity can overwhelm pressure and shear forces, causing collapse. If that collapse is fast and massive enough, a large gas clump can form directly, bypassing the slow incremental growth of a solid core. This is disk instability, and it produces objects that look like planets in orbit, but behave more like stellar embryos that never fully matured. The problem is that disk instability was once thought to be rare. Simulations suggested it required unusually massive disks, very specific temperature conditions, and rapid cooling. But the growing catalog of extremely large exoplanets is forcing scientists to reconsider. The universe may be far more efficient at building giants than our early models assumed. And if that is true, then the largest planet ever discovered may not be a freak occurrence, but an extreme example of a common process. There is another complication. The star these giant planets orbit matters. Massive planets tend to form around massive stars, where disks are larger and richer in material. But observations show that some super-giant planets orbit relatively ordinary stars, even stars smaller than our Sun. This is unsettling. It implies that planet formation is not just a matter of available mass, but of timing dynamics and feedback between the forming planet and its environment. As a giant planet grows, it reshapes the disk around it. Its gravity opens gaps, redirects material, and alters the flow of gas. In some cases, this feedback limits growth. In others, it accelerates it, funneling even more material onto the planet. The largest planet ever discovered appears to have experienced runaway growth, a phase where accumulation outpaced any stabilizing mechanism. Understanding how that happens is now one of the central challenges in planetary science. But size is only part of the story. What makes this planet transformative is not just how big it is, but how it behaves. Its atmosphere is not a simple extension of Jupiter's. Under extreme gravity, atmospheric layers compress in unfamiliar ways. Temperatures soar. Chemical reactions proceed under pressures rarely encountered elsewhere. Molecules dissociate. Clouds form from exotic materials. In some of these worlds, iron rains from the sky. Silicates condense like soot. Weather systems stretch across distances larger than entire planetary orbits. These atmospheres are laboratories of physics. They allow scientists to test models of fluid dynamics, radiative transfer, and chemistry under conditions impossible to reproduce on Earth. When astronomers analyze the light passing through or emitted by such a planet's atmosphere, they are not just characterizing an exotic world. They are probing the limits of physical law as it operates on planetary scales. The largest planet ever discovered also forces a reevaluation of the boundary between planets and brown dwarfs. Brown dwarfs were once considered rare, occupying a narrow mass range between stars and planets. But as surveys improve, it has become clear that objects in this range are abundant. Some orbit stars like planets, some drift freely through space, some form in isolation, others in disks. Classification based solely on mass now seems inadequate. This has led to a shift in thinking. Instead of asking whether an object is a planet or a brown dwarf, astronomers increasingly ask how it formed. Formation history may matter more than size. A massive object formed in a disk may be considered a planet even if it exceeds traditional mass limits. A smaller object formed through stellar collapse may not. The largest planet ever discovered sits at the heart of this debate. It is forcing scientists to confront the possibility that our categories are descriptive conveniences, not fundamental truths. There is also a broader implication for planetary systems as a whole. Giant planets influence everything around them. Their gravity sculpts asteroid belts, redirects comets, and destabilizes or protects inner worlds. In our own solar system, Jupiter's presence likely played a role in shaping Earth's impact history. A planet even larger would exert an even greater influence. Systems hosting such giants may be hostile to small, stable, Earth-like planets. Or they may, under certain conditions, shield inner regions from catastrophic bombardment. This raises questions about habitability, not because the largest planet itself could support life as we know it, but because its existence alters the architecture of its system. If supergiant planets are common, then the distribution of habitable worlds may be very different from what early models predicted. Some systems may be dominated by a single massive planet, with little room for stable terrestrial companions. Others may host giants on wide orbits, leaving inner regions relatively undisturbed. The discovery also feeds into a deeper narrative about scale in the universe. Humans evolved on a small rocky world orbiting an average star in an unremarkable galaxy. Our intuitions are tuned to modest sizes and gentle gradients. But the universe operates comfortably at extremes. It builds planets that dwarf anything we imagined. It constructs stars millions of times more massive than the Sun. It creates black holes that warp spacetime itself. The largest planet ever discovered is a reminder that even familiar categories can hide astonishing extremes. There is a temptation to see such discoveries as curiosities, interesting but ultimately irrelevant to everyday life, but that misses the point. Science advances not just by confirming what we expect, but by confronting what we do not. Every time an object like this is found, it forces a recalibration of theory. It refines our understanding of probability. It tells us something about how common certain outcomes are in the cosmic lottery. And there is a subtle philosophical shift embedded in this process. When we discover the largest planet ever discovered, we are not just learning about that planet. We are learning about the distribution of possibilities in the universe. We are mapping the edges of what is allowed, and those edges inform everything from how we model galaxy formation to how we estimate the prevalence of life. The discovery of the largest planet ever found does not end with classification debates or formation theories. Its true impact unfolds in what it forces astronomers to do next. Once an object stretches the limits of known physics, it becomes more than a data point. It becomes a calibration tool, a stress test for the entire framework through which we observe and interpret the universe. And in that sense, this planet is already reshaping the future of astronomy. One of the most immediate consequences is how it changes the way we search for planets at all. For decades, detection methods were optimized around assumptions drawn from our solar system. Moderate-sized gas giants, Earth-sized rocky worlds, predictable orbital distances. But supergiant planets break these assumptions. Their sheer mass exaggerates certain signals while masking others. They can dominate the motion of their stars, distort circumstellar disks, and produce observational signatures that were once dismissed as noise or misinterpreted as stellar activity. In radial velocity surveys, for example, extremely massive planets can induce stellar wobbles so strong that they resemble binary star systems. Early surveys often excluded such signals, assuming they were not planetary in origin. Now, with confirmed detections of planets approaching the brown dwarf boundary, astronomers are revisiting archival data. Signals once discarded may, in fact, be evidence of additional giants waiting to be recognized. The largest planet ever discovered is prompting a quiet reanalysis of the past. Transit surveys face a different challenge. A planet of enormous size produces a deep, unmistakable dip in starlight. At first glance, this should make detection easy, but such deep transits can also mimic eclipsing binary stars, leading to false positives. As a result, some of the most extreme planets may have been filtered out by automated pipelines designed to eliminate stellar imposters. The lesson is subtle but profound. Our tools do not merely observe the universe. They reflect our expectations about it. This realization is driving changes in how future surveys are designed. Instead of optimizing for Earth analogs alone, astronomers are expanding parameter spaces. They are training algorithms to recognize extreme systems. They are building models that allow for worlds that do not resemble anything we have seen before. The largest planet ever discovered is acting as a reminder that rarity does not equal impossibility. There is also a technological consequence. Studying such a massive planet in detail requires instruments capable of extraordinary precision. Its atmosphere, heated and compressed by immense gravity, emits and absorbs light in complex patterns. Interpreting those patterns demands high-resolution spectroscopy across multiple wavelengths. This has placed new demands on observatories both on Earth and in space. Space-based telescopes, free from atmospheric distortion, are particularly well suited to this task. They can isolate faint planetary signals and track subtle changes over time. The largest planet ever discovered has already become a target for repeated observation, not because it is representative, but because it is extreme. Extremes clarify physics. They amplify processes that are otherwise difficult to measure. Ground-based observatories are evolving as well. Advances in adaptive optics allow telescopes to correct for atmospheric turbulence in real time, bringing distant worlds into sharper focus. Massive planets on wide orbits are especially attractive targets for direct imaging. Unlike smaller planets, they emit enough infrared radiation to be detected against the glare of their stars. Each successful image is not just a picture, but a test of atmospheric models and cooling theories. As observational capabilities improve, another implication comes into focus. The largest planet ever discovered may not hold the record for long. In astronomy, records are provisional. They last only until better instruments reveal something larger, more massive, or more extreme. This is not a failure of measurement. It is a sign of progress. The universe has always been this vast. We are simply becoming better at seeing it. This expectation is already influencing the goals of next-generation telescopes. Designs now account for the possibility of detecting planets at the edge of classification, objects that sit between traditional categories. These telescopes will not just count planets. They will characterize them, mapping their atmospheres, measuring their temperatures, and tracking their evolution over time. And evolution matters. Giant planets do not remain static. Over billions of years, they cool, contract, and sometimes lose mass. Their early lives are violent, marked by intense radiation and rapid change. The largest planet ever discovered offers a glimpse into these early stages, especially if it is relatively young. By observing its current state, astronomers can test models of planetary aging and thermal evolution. There is also a statistical consequence. As extreme planets enter the census, they reshape population studies. The distribution of planet masses, sizes, and orbits informs theories of formation. If supergiant planets are more common than expected, then the average outcome of planet formation shifts. What we once considered rare may be typical under certain conditions, and what we considered typical may be an artifact of limited observation. This feeds into a larger narrative about uncertainty in science. Astronomers do not discover the universe all at once. They sample it unevenly and imperfectly. Each new class of object fills in part of a larger picture. The largest planet ever discovered occupies a corner of parameter space that was once blank. Its presence forces us to redraw contours we thought were fixed. Beyond methodology and theory, there is a quieter consequence that reaches into public understanding. Planets are often portrayed as potential homes, places of familiarity scaled slightly up or down. But a planet of this magnitude resists that framing. It is alien not because it is distant, but because it violates intuition. Its existence expands the emotional scale of the universe. It reminds us that the cosmos is not optimized for comfort or relatability. This matters because public imagination shapes scientific priorities. When people grasp that planets can be unimaginably large, that systems can be dominated by objects unlike anything in our solar system, curiosity deepens. The question shifts from finding another Earth to understanding the full range of what nature builds. The largest planet ever discovered contributes to that shift, not through spectacle alone, but through implication. It suggests that our solar system may be one quiet outcome among many louder possibilities. It hints that planetary systems can be shaped by giants far more dominant than Jupiter. And it underscores a recurring theme in astronomy. Every time we believe we have mapped the boundaries of the possible, the universe gently pushes back. As we move forward, the importance of this discovery will not be measured by its size alone. It will be measured by how it changes the questions we ask. How many more such planets exist? How do they influence their systems? Where do we draw lines and why do we draw them at all? The largest planet ever discovered does not answer these questions. It sharpens them. And in science, that is often the most powerful change of all.